Hello, everyone, and thank you for so much for tuning in. Today, we're diving into cosmology, the that explores how everything began, how it evolved, and where it all might be headed. Think of this as a story of the universe, from the chaos of the Big Bang through the birth of stars and galaxies, all the way to the theories about how it could end. Along the way, we'll investigate things such as black holes, wormholes, dark matter, and more. I hope this tour of the cosmos leaves you thinking a little bigger. Section 1, Intro and Big Ideas. What is cosmology? To start, let's talk about what cosmology actually is. Cosmology is the scientific study of the universe as a whole. Instead of looking at individual stars or planets, cosmologists zoom out and study the universe's origin, its structure, how it has changed over billions of years, and what its long term future might be. Cosmology began as a philosophical idea thousands of years ago, but in the last century, it has transformed into a precise science powered by physics, telescopes, satellites, and mathematics. Today, cosmology helps us answer questions like, how did the universe begin? Why does it look the way it does? What is it made of? And what will happen to it in the far future? Why cosmology matters. So, why should we care about cosmology? Why study things that happened billions of years ago in places we may never reach? Cosmology is about understanding the biggest questions we can ask. Where did everything come from? Where are we going? Why does the universe look the way it does? But it's more than just space trivia. It is how we learn about our own origins. Cosmology connects physics, astronomy, math, and even philosophy. It forces us to think bigger, to ask better questions, and to chase answers that seemed impossible. Plus, the tools and ideas developed for cosmology have real world impact, from satellite tech to computer modeling to even medical imaging. And let's be real, there's something just awesome about peering back into the past, billions of years, to watch the universe unfold like a story. That's what makes cosmology matter. It's not just science, it's the story of everything. So, now that we have a better understanding of what cosmology is, let's go all the way back to where it all started, the Big Bang. Scientists first confirmed that the universe is expanding somewhere around the 1920s, where they observed galaxies moving apart. The farther a galaxy is, the faster it recedes. This led to the idea that everything used to be closer together long ago, i.e., a Big Bang. So, despite the name, the Big Bang was not an explosion in empty space. It was the rapid expansion of space itself from an extremely hot and dense initial state. Unlike a bomb going off at a point, the Big Bang happened everywhere in space at once. Space itself expanded. The first tiny fraction of a second, temperatures were so high that the laws of physics as we know them did not work normally. All matter, energy, space, and even time were compressed into a state that is still not fully understood. The Big Bang marks the moment the universe began expanding and cooling, eventually allowing structure to form. After the Big Bang, the universe passed through several distinct eras that help us understand what was happening during the first moments of cosmic history. The very first of these is the Planck era. This era lasted from around time equals 0 to about 10 to the minus 43 seconds, which is a very small amount of time. But during this time, the universe was so hot and dense that gravity and quantum mechanics were essentially merged. Space time itself fluctuated like boiling water. We do not have a complete theory to describe this era yet. It is one of the biggest mysteries in physics, but we know that whatever happened here set the stage for everything that followed. Next comes cosmic inflation, one of the most notable events in the early universe. Inflation was a period where the universe expanded very rapidly, far faster than the speed of light. You may wonder, how is such a thing possible? Considering we know that matter cannot move faster than the speed of light, nothing can. But the reason this was possible, it was not the matter itself moving faster than light. It was space stretching and expanding rapidly. So, space itself was moving faster. Now, inflation smoothed out the universe and made it extremely uniform and amplified tiny quantum fluctuations into slight differences in density. These slight differences eventually became the seeds of galaxies. Section 2. How structure formed. Long before the first atoms formed, the first atomic nuclei formed just minutes after the Big Bang, in a brief period of primordial nuclear fusion. The newborn universe produced hydrogen and helium. Once inflation ended, and the universe continued cooling over thousands and thousands of years, something important finally became possible, which was the formation of the first atoms. At first, only the simplest nuclei existed, hydrogen and helium. But, like we said, after about 380,000 years after the Big Bang, the universe cooled enough for these electrons to attach to these nuclei, forming neutral atoms. This transition actually allowed light to travel freely for the first time. The reason light couldn't travel freely before neutral atoms formed was because these free electrons kept scattering it. But once these electrons were captured into the atoms, the fog lifted and light could finally move across the universe. Now, a cool thing to note is that light still fills the universe today as the cosmic microwave background, or CMB. You can look at it as basically the oldest photograph in existence, like a baby picture of the cosmos. The CMB showed slight temperature variations that tell us somewhat what the early universe looked like and confirm many predictions of our Big Bang model. Now, after this, the cosmic dark ages ended when gravity pulled clouds of hydrogen together to form the first stars. These first stars were enormous compared to stars like our sun. They burned quickly, lived short lives, and exploded violently, creating heavier elements like carbon, oxygen, and iron, the elements that make life possible. Here's a slide showing some of the stars in our universe. We have Sirius, Regal, Arcturus, sorry, I don't know how to pronounce all these, Betelgeuse, just so you have an idea of what these stars look like. With stars lighting up the cosmos, gravity continued shaping the universe. And as stars gathered, galaxies began to form. Collisions, mergers, and swirling cosmic debris helped create the beautiful structures we see in the universe today. Spirals, ellipticals, clusters, and even superclusters of galaxies. As we could see in this slide, here are pictures of different galaxies from across our universe. You could see the different kinds that we have. Now, meanwhile, around many of these stars, Leftover disks of dust and gas collided and clumped together to eventually form planets. Some were small and rocky, others large and gaseous. Over billions of years, galaxies matured, stars formed and died, and solar systems were born. Section 3. The universe today. So, we have gone from a speck of infinite density through inflation, atoms forming, stars igniting, and galaxies assembling, all the way to where we are today. Today, we live in a universe that's about 13.8 billion years old. There are billions of galaxies, and each galaxies contain billions of stars. It's almost impossible to really wrap our heads around how big and full the universe is. Us ourselves, we are in a pretty average galaxy called the Milky Way, and in one of its quieter neighborhoods, there's a little solar system with one star, 8 planets, and there's at least one planet wondering how it all began. But the story is not over. Far from it. The universe is still expanding, faster than ever. And we have realized that most of the stuff out there, we cannot even see. That is where things like dark matter and dark energy come in. So, let us dive into those cosmic mysteries next. Dark matter. Dark matter is one of the biggest cosmic mysteries today. We cannot see it, touch it, or photograph it because it does not interact with light at all. But we do know it is there because of how galaxies behave. When scientists studied galaxies, they found something strange. The stars on the edges were spinning way too fast, fast enough that the galaxy should fly apart. But it did not. Something unseen must be providing the extra gravity holding it together. That something is what we call dark matter. It does not glow, shine, or absorb light. It is completely invisible. But its gravity helps glue galaxies and galaxy clusters together. Scientists think it might be made of exotic particles we have not discovered yet. It is like the universe's hidden scaffolding, shaping how everything moves, clumps together, even though we still do not know what it really is. Now, while dark matter holds things together, dark energy is doing the opposite. It is pushing everything apart. Back in 1998, scientists were studying exploding stars called supernovae. They expected to find that the universe's expansion was slowing down, but they were shocked to find the opposite. The expansion was actually speeding up. That mysterious force is causing acceleration. Is what we call dark energy. We do not know what it is, much like dark matter, but it acts kind of like an anti-gravity and is not rare. It makes up almost 70% of our entire universe. 68 to be more exact. Dark energy plays a huge role in the future of our universe. If it keeps pushing, galaxies will get farther and farther apart. Over time, the universe could grow colder, darker, and emptier. So, even though we cannot see it, dark energy may control how the universe ends. Section 4. Future of the universe. Now, we have looked back in time to see how the universe came to be as of today. We have looked into certain cosmic mysteries such as dark matter and dark energy. So, let us look forward in time to see what the end of the universe may look like. In this scenario, called the heat death scenario, you can also call it the big freeze. Due to this dark energy, the universe keeps expanding forever. All the stars will eventually exhaust their fuel and burn out, and no new stars can form once the raw material is used up. Galaxies that aren't gravitationally bound to each other will recede increasingly far apart as space continues to expand. Even over trillions of years, the cosmos will grow colder and darker. The temperature of the universe will approach absolute zero. Essentially, all energy becomes spread thin and reaches maximum entropy. So, there's no thermodynamic free energy sources left to sustain processes. In other words, no usable energy remains, what we call a heat death. At this point, nothing happens in the universe anymore in a practical sense. This big freeze outcome is considered by scientists to be the most likely fate of the universe given what we know today. The reason is that the observations of distant supernovae, the cosmic microwave background, and galaxy distributions all indicate our universe is dominated by dark energy and will expand indefinitely rather than recollapse. In particular, if dark energy remains a constant force, the universe expansion will continue accelerating forever, leading to the long-term heat death scenario. In this grim but quiet ending, the universe simply fades out. Stars die, galaxies drift into darkness, and even black holes eventually evaporate over immense timescales, leaving behind a cold, nearly empty cosmos. Now, this is just one possible ending to our universe. Scientists have come up with other theories that could end our universe. Just the heat death is the most likely. So let's look into some others. The Big Rip. One possible fate of the universe is the Big Rip. It's the most extreme, over-the-top ending we've imagined so far in cosmology. In this scenario, the expansion of space doesn't just continue, it accelerates uncontrollably. Dark energy grows stronger over time, pushing galaxies apart faster and faster until the expansion outruns every force we know. First, galaxy clusters get pulled apart, then individual galaxies, then solar systems. Eventually, even the atoms inside your body wouldn't feel safe. They get torn apart as space itself stretches beyond what any force could hold together. The really creepy part, this happens everywhere at once. Space doesn't rip from a single point, it rips in all directions, shredding the universe down to its most fundamental pieces. Again, it's our most dramatic ending. Not with a bang, not even with silence, but with the universe literally tearing itself apart. Now, let's flip the script entirely. Instead of the universe flying apart, imagine expansion slowing, stopping, and then reversing. In the big crunch, gravity eventually will take over. The universe starts pulling inward, and everything, galaxies, stars, planets, begin falling towards everything else. Galaxies collide in massive fireworks of radiation. Stars are packed closer and closer until temperatures and pressures skyrocket over immense timescales. The entire cosmos collapses back into a single, unbelievably dense point. It would be like watching the Big Bang play in reverse, a cosmic rewind button per se. And at the end of the collapse, some theories say the universe could bounce and trigger a new Big Bang, meaning our universe might be one cycle in an endless cosmic rhythm. So, here's where things get wonderfully weird, you could say. The multiverse. This idea states that Our universe, the thing containing hundreds of billions of galaxies, might actually just be one bubble in a much larger cosmic foam. Other universes could exist with different physical constants, different particles, different dimensions, or even no matter at all. Some might be chaotic and uninhabitable. Some might be almost identical to ours, different by single tiny details. And the infinite multiverse, every possibility might exist somewhere. The idea comes from things like string theory, quantum fluctuations, and the rapid expansion right after the Big Bang, also known as inflation. It's not proven, but it forces us to confront almost a humbling idea. Our entire universe could just be one small chapter in a much bigger story. So, cosmology attracts some of the most creative ideas in science. Here are a few of some wild ones. Like we said, the bounce from earlier, the cosmic bounce. Instead of a single beginning and end, the universe might just constantly repeat itself. Big Bang to expansion, back to contraction, to the Big Crunch, and then back to another Big Bang. The whole cosmos might be eternal, pulsing, sort of like a heartbeat. Let's look at vacuum decay. If the universe is sitting in a false vacuum, a temporary energy state, it could suddenly snap into a lower energy true vacuum. That transition would rewrite every law of physics instantly. Don't worry, if it ever happened, we would never see it coming. Some thinkers suggest that the universe might be a super advanced simulation created by another civilization. Almost like a civilization's super advanced video game. This is more philosophy than physics, but it makes us question what reality really means and why the laws of physics look so mathematical in structure. Cosmology doesn't just explain the universe, it reminds us how much we don't know. Section 5. Cosmic Wonders and Fun Facts. Now let's talk about one of the most mysterious objects in existence. Black holes, cosmic monsters. Black holes form when massive stars collapse under their own gravity, squeezing their mass into a point of almost infinite density, which we can call a singularity. Around them is the event horizon, the point where escape becomes impossible, even for the fastest moving thing in the universe, light. We can't see black holes directly, but we can catch them based on how they twist space and light around them. Stars orbit strangely, gas spirals in and superheats, and space itself bends like a trampoline holding a bowling ball. You can imagine it almost like an elephant underneath a blanket. You can't see the elephant, but you can see the effect it's having. The gravity near a black hole is actually so strong that time itself slows down. A clock near the event horizon would tick slower than one far away. This isn't sci-fi or nothing like that. GPS satellites need relativity corrections for much weaker gravitational differences here on Earth. Spaghettification. This is a cool idea. Have you ever wondered what would happen if you fell into a black hole? Well, if you fell towards a black hole, the gravity would pull harder on your feet than your head. This difference in force would stretch your body like a spaghetti noodle, aptly named spaghettification. So, in a stellar mass black hole, you'd be torn apart long before reaching the center. In a supermassive black hole, gravity at the horizon is gentler. You might not even feel anything at first, until much later, when the tidal forces skyrocket. Supermassive black holes. At the center of most galaxies, including the Milky Way, we think there are supermassive black holes, millions of times the mass of the Sun. Our galaxy's central black hole is called Sagittarius A, and we've even taken a picture of it. Well, at least the glowing ring around it. Black holes actually reshape the universe and can even reshape our imaginations. Wormholes. So, if black holes are nature's monsters, wormholes can be looked at as nature's shortcuts. A wormhole is a hypothetical tunnel that connects two distant points in space, or even in time. Picture bending a sheet of paper so that two distant spots touch and punching a direct tunnel between them. That's the idea. Einstein's equations do allow for wormholes, but they would be very unstable, collapsing almost instantly, unless you use exotic energy to hold them open. Whether nature actually makes these things is unknown, but the idea fuels both theoretical physics and even sci-fi movies and TV shows. A real wormhole would change everything: travel, communication, exploration, but until we find one, they remain one of the universe's biggest what-ifs. And here's a better look at that picture. So you could see this blue and purple. Imagine that as the fabric of space itself. And you could see how the paper analogy really works here, to take a so-called shortcut. Okay, fun cosmic facts. To end on a high note, here are some cosmic fun facts that may blow your mind. Neutron stars are ridiculous. Neutron stars, which are the remnants of supernova explosions, can spin over 700 times per second. Their surface gravity is so intense that a teaspoon of neutron star material would weigh about 4 billion tons on Earth. The coldest place in the universe is actually in a lab. We've created temperatures just a few billionths of a degree above absolute zero, colder than any natural place in space. At these temperatures, atoms start behaving like one single superatom, a state of matter called a Bose-Einstein condensate. The Milky Way smells like rum and raspberries. At the center of our galaxy, scientists have detected ethyl formate, a molecule that tastes like rum and smells like raspberries. So, yeah, some spots in space have a weird aroma. Space isn't silent. While space is mostly a vacuum, we can detect sounds from cosmic events using gravitational waves. These waves come from things like merging black holes or neutron stars, and we've actually heard them recorded by LIGO. I may say that. If the Milky Way were the size of a dinner plate, Andromeda would be another dinner plate over 2,000 kilometers away, about the distance from New York to Florida, and between them mostly empty space. But here's the wild part. The observable universe contains about 200 billion more dinner plates, each one a galaxy containing hundreds of billions of stars. So, the universe is bigger than you can imagine. The observable universe spans about 93 billion light years, but it's actually larger than its age suggests, because space-time itself expands every moment we speak. More of the universe comes into view, and more of it stretches beyond reach forever. So, conclusion. Our place in the cosmos. We have taken quite a journey from the explosive beginnings of the Big Bang to the birth of stars and galaxies, all the way to the mysterious possible endings of the universe. Along the way, we have learned about some strange objects, black holes, dark matter, wormholes, even the idea of other universes. But it's more than just facts. Cosmology shows us something deeper. It helps us understand where we came from, how everything fits together, and where we might be headed. The universe is almost unimaginably huge, ancient, and mysterious. And yet, somehow, we are part of it. One tiny planet, around one star, in one galaxy, and here we are trying to figure it all out. And that's what makes science beautiful. There's always more questions, always more to learn. I'm sure there's plenty of things I've not explained throughout this presentation due to brevity and other circumstances that may have you curious. So, I say, stay curious and keep asking big questions. Thank you for watching. If you guys have any questions, I'd love to try to answer them in the comments. Thank you again.